Thank you very much. Thanks for everybody to be here, and thanks for Carl to organize it, and the organizers, well, to organize that I'm invited here as well. So we'll talk about some new approach to the quantum marginal problem, and let's start. So there's three parts: introduction, general subject. I will talk about maximally entangled states, or some set of certain maximally entangled states, and then some new operator inequalities, and you'll see that this all kind of fits together with this quantum marginal problem, which I will explain what it means. So let's start with the introduction. And the natural starting point for this quantum marginal problem is actually entanglement. So what is this? Schrödinger described it as the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. So even if we know exactly what the complete thing is, we don't necessarily know exactly what its specific subsystems are. That is, they are less determined than the complete thing. So, of course, for quantum states, the whole is the joint state, say here a bipartite state, psi AB, and the parts are its marginals obtained by taking the partial trace over the density matrix formed by psi AB, and then we get the marginal rho A. Let's do this a bit more formal. So for a pure quantum state, it says it's entangled if it cannot be written as the tensor product of one-body states. So psi AB entangled cannot be written as psi A tensor psi B. And for mixed states, so density matrices, this naturally extends with convex combination. So a mixed state that is entangled cannot be written as a convex combination of tensor products of individual density matrices. So the paradigmatic example of a maximally entangled state is the so-called belt state of two parties, superposition of 0, 0 and 1, 1, or spin down, and spin up, spin up. And so what's interesting here, its reductions are maximally mixed, so they're uniform. If we trace out this state over one party, so we trace out over the subsystem B, we get the subsystem on A, the density matrix, and this is proportional to the identity, so we don't know anything about this subsystem. It's completely uniform. The same with the other subsystem, but the complete state is pure and determined. And this is exactly what Schrödinger, or what he said nicely. So one has the best possible knowledge about the whole, so we know exactly what the complete state is, but absolutely no knowledge about its parts, because they're uniform. So this naturally leads to the so-called quantum marginal problem, which is a kind of a quantum puzzle. And to illustrate it, I want to focus your attention on this picture. This is the cover.
Pointer down there next to the table.
It's fine, I'm tall enough. Thanks.
You are tall enough, yeah, but
I'm in the picture. Okay, so this is the cover from Gödel, Escher, Bach, this book by Douglas Hofstadter. And we see those are three-dimensional objects. So they're kind of here wooden pieces with cutouts, and their projections are certain letters. And one could ask the question, well, does there always, if I choose some set of letters to be their projections, can I always find some kind of joint object whose projections are these letters? And for three-dimensional objects, this is actually true. But we see this is kind of, this is somehow a classical perspective of this marginal problem, because in the marginal problem, we are in some way given the projections, which are the reduced density matrices, and we are given different ones, and we ask if a joint object exists or not. Yeah? So it's some kind of puzzle. We are given certain aspects, or the marginals of this complete object, and we ask if a complete object exists which has these parts. So for certain questions, like given a set of marginals, rho S, so S is here some certain subsystem with a set of these marginals. Does there exist a compatible joint state, which could be either mixed or pure? We could ask if such joint state exists, if it then also is unique or not. This is relevant for ground states of Hamiltonians, because, of course, if certain ground states have the same marginals, and so if there's many states having the same marginals, and the Hamiltonian is local as well. So,
question number one.
Yes.
You have to first to know that the row with sub S are the marginal states. Otherwise, if you have a density matrix, how do you know that it is related to something else?
This is exactly the question.
You know,
So
the answer is obvious. It must exist if you know that this is the marginal state.
Yes, but the
marginal
question...
state, by definition, comes out from some
Yeah,
state.
but the question here... Let me
don't
answer.
know it,
Let me
but
answer.
it exists. How
Let-
do you know that the matrix rho S is a marginal?
So let me answer. Exactly this is the question. How to determine, if I have a set of marginals, if there's a joint state that exists. So it's a non-trivial question.
You have a set of reduced density matrices, and you are asked, you should not call them marginals from the beginning, because this suggests that they actually come from.
Okay, we call them density matrices.
Call them
yeah?
reduced states, and then it's okay.
Okay, let's call them putative marginals, hypothetical marginals.
To know that these are reduced
If there's a single density matrix, is definitely a marginal sum. Okay? But if there are two, it's not so clear.
Maybe let me continue, and then things will be clear up. Okay, so let's replace everywhere where I write marginal. Let's replace it by the word a putative marginal or a hypothetical marginal. So some density matrices which is smaller than the joint state. Okay, and then hopefully this is clear. So we're given this set of putative marginals, and we ask if a joint state exists. We ask if it would be unique or not. So this is relevant for knowing the degeneracy of ground states or not. And we could also ask if we have some explicit reconstruction formula. So here's some known results. This is the first one by Coleman. There it was called the end representability problem. And it says that some one-body marginal, rho, is a marginal of a system of n fermions, even only if each of its eigenvalues lambda I is smaller or equal than 1 over n. So the condition is purely the condition that rho can be the reduction of an n-partite fermion system is completely dependent on the spectrum of the density matrix. If this condition is fulfilled, then there is indeed a joint state, having that one-body particle as a marginal. And there...
Know that there is a system of n fermions.
Yes.
Yeah, so
This is an extra information. It's not just rho that you know, but also that it is a marginal.
Exactly. So this is a
precisely my point.
this is a partial
Have a
result.
density matrix, how do you know it's related to
No, but
something
this is
else?
just a partial result.
Okay. And then this was generalized by Higuchi and al. To others to systems of qubits, and then by Bravi and Franz and Borland and Davis, and so there's many people that are working on that in terms of so-called Polygon inequalities, which are very similar to that one, so they constrain the spectrum of the reductions. So one can generalize this to say n-partite qubit systems. Yeah. And in principle, Klyatschko solved this quantum marginal problem in the case of such non-overlapping marginals. So non-overlapping in the sense of that the subsystems these marginals should live on, they don't overlap. Yeah, so this problem is completely solved by Klyatschko. But of course, we can now ask, well, what happens if we have marginals that overlap? So we have, say, implicitly completely solved.
Because the inequalities which you get from this solution, there are so many redundant inequalities that applying a solution of Klyatschko to systems of more than 3 fermions with, I think, 9 levels is impossible.
There are many inequalities.
It's
It's not practical, I agree, but it's implicitly solved. So Klaczek gave a recipe how to solve it, but of course, you're right. It's not like easy to evaluate. It's about overlapping marginals. So overlapping, I mean, in the sense of like, so we have system A, B, and C, and then we could have, okay, it's not a nice triangle, but we could have the density matrices rho AB and rho AC as an example, and rho BC, so they overlap. Some systems, subsystems are the same. So as you could imagine, this is somehow an even more difficult question. Now there's a theorem by, okay, there's a strong subjectivity, or in this case it's the equivalent formulation, weak monotonicity, that was derived by Lieb and Ruska in '73 and later applied to this problem by Linden. So if it's a necessary condition, this marginal problem, if rho AB, rho AC, and rho BC are compatible with a joint state in three parties.
I'm confused with the notation. Rho with subindices BC means that you have traced the degrees of freedom of B and C, or A?
I traced over subsystem A. So,
Yeah, never mind. I mean, follow that. I mean, you trace over
so if I trace over B, rho A,
B and C.
yeah, so the index here tells
But
me,
if you have a tree, then this I know.
well, it's the same, right?
Tree, this is
So if I have rho A, B, C,
Which subsystems are?
exactly.
are trace or they are not trace?
So, yeah.
The
Okay, all right.
subsystem
Okay.
to which
Okay,
it
that,
relates.
This should make it clear. Right? So they live on two, otherwise it would be the same as before, right? You wouldn't have any overlapping margins. So here you have overlap. A and A, AB, AC, and BC. So if rho AB, rho AC, and rho BC are compatible with a joint state rho ABC, then we have this necessary condition on the von Neumann entropies of the subsystems. Okay. This S of rho is the von Neumann entropy. Yes, it's a kind of information theoretic condition that these marginals can fit together, but it's only necessary, not sufficient. I'll give you another example of a theorem by Butterley, Siperi, and Schultz. It's the same question, rho AB, rho AC, and rho BC are compatible with a 3-qubit joint state. Then the following operator inequality holds. So here, it's a bit different than before. Rho A means rho A tensor with identity on BC. Yeah? So it's the padded subsystems. The dimensions are the same. Yeah? So I take the complete state, trace out BC, and then I pad it with identity on BC. So I take here a slightly different notation than up here. Right? Otherwise, it also wouldn't make sense because they would have different dimensions. So I tensor with identity, so they get the same dimensions. So those are all 8 by 8 matrices. So the claim is that if they're compatible with a joint 3-qubit state, then this operator inequality holds. So this operator with these minus signs and plus signs has to be positive semi-definite, and also its eigenvalues have to be smaller or equal than 1. It's somehow also non-trivial, and there's some kind of different flavor to it than the previous things. So the first one I showed was in terms of spectral, in terms of the spectrum of the reductions, so the eigenvalues. This above is some kind of information inequality, an entropic inequality, and the last one is an operator inequality. So they're all kind of a different flavor to it. And so during my talk, at the end you will see I will generalize this. Okay, let's go to the part 2, which doesn't seem connected, but actually is. It's about maximum entangled states. And you'll see that this question about the existence of certain maximum entangled states is in some way a quantum marginal problem. Because we ask, does there exist some state having maximal entanglement that implies on n parties? Yeah? And that implies something for the marginals, and of course this can be phrased as a quantum marginal problem in the sense of if these marginals given, we ask if a joint pure state exists with these properties. Yeah, will become clear. So this was motivated by paper.
There were diagonals in case of hexagon, whereas no diagonal in case of pentagon.
Okay, so these are just illustrations. These are graph states. It's not important. These are just illustrations of the states we know exist. They can be represented in terms of graphs, and they tell us how to produce the graph in terms of gates. Yeah. So it's just a picture. It's not super important. For those who know graph states, yeah, these are the corresponding graphs to those states, which we'll see later play a role. So this question was motivated by a paper by Eugene Sudbury, namely how entangled can two couples get? So if you have two parties alone, it's obvious we have the Bell state that is maximally entangled. If you have four parties and we want maximal entanglement, there are a lot of constraints. So we want maximal entanglement for these and these pairs and these and these and the other two pairs, and then we have maybe one pair versus the rest. And it's not obvious if it's possible or not to do that. So in fact, it's not possible. And
you will only consider in this talk finite dimensional Hilbert space.
yes. And so this question is then answered negative for 4-qubit systems. The exact definition of this maximal entanglement we'll go into. Because if I ask how entangled can 4 parties get, I have to ask, well, what is maximal entangled for multipartite systems? And for this to understand, we have to look at why the Bell state is considered to be maximally entangled. And the answer would be that every other pure state.
What is 5 plus?
So this, sorry, from the Bell state. The Bell state 5 plus.
Okay.
This is what
Has anything to do with the upper?
no, this one.
Oh, this is 5 plus.
That's this. That's 5 plus.
Yes.
It is 5 plus or not?
Yes, it is 5 plus.
Small phi are the same.
Oh, I used the small phi and capital phi. Very good. Thanks, Carol. Okay, so this 5 plus.
You will explain what you mean by local operation.
Yeah, let me first explain the slide. Okay.
There are so badly educated individuals like me that they don't know it.
Yeah. Let me first actually explain the slide before answering questions. So we have to ask why the Bell state is maximally entangled, or considered to be maximally entangled, and the answer would be that every other pure state, so some other pure state psi, can be obtained from the Bell state 5 plus by some set of operations, which we call local operation in classical communication. So what is this? A local operation is what each of the two subsystems, so you have A and B, they can be Alice and Bob, they're in two distant labs, they have each a part of this Bell state, and there are all kind of operations they can do locally in their lab. So they could apply some gate to it, some unitary operation, or they could...
They will only act on this particular substance.
Exactly. It's everything that Alice
Why
or
not
Bob...
call it local? Never mind. It's important to understand the words, you know. You have to understand that this is not the professional audience. Quantum computers or whatever. We need to understand the words.
Okay.
Otherwise, the
Words and symbols, if you use them with and give explanation only on demand, we are lost.
Okay.
Local, I think, is simple because they are locally in one laboratory.
Exactly. So we have two-partite system. Okay, then let me explain again. Let me explain again. So we have a two-partite system. In principle, those two parts of the system could be infinitely far away. And we call one subsystem A and the other subsystem B. And then the local...
This goes beyond the definition of the state, where there is no X in the state, which
X?
comes
But
with...
now he's defining local operation.
Yeah.
Yeah, but
The only excuse is that neither speaker nor we invented this name.
Maybe. Okay, so let me clarify again. Local operation in that context means we have a two-partite system. A and B are the two parties, And a local operation is something that either A can do in her lab, or B, Bob, can do in his lab. Yeah? So they can do something locally on their part of the system. Some operation.
So it does not affect the other
Two-level system.
Well, it's an operation that one person does his state or other. It can affect. Okay?
What is the story about the Faraday and
For historical reasons.
Exactly. And classical communication is just the fact that the two
for confusing reasons?
the two people can communicate with their labs by classical means. Yeah, so they can talk to each other and ask, okay, what do we do on our side of the state? Okay, so this is some kind of also the resource formulation of entanglement. Is that clear or? Good.
We understand more or less what is local and what is classical. Because there was also the word classical.
Yeah, as I said, I said this at least twice. So,
This is the communication that you can do by ordinary phone.
By ordinary what?
Email.
But
For example, iPhone.
Yeah, well, of course, I prefer a Chinese army who is less. But
Lukasz,
how
I
the
think-
spins communicate?
Łukasz, I think it is the following. So, without using the names local, communication, and so on, you made some operation on one of these two things,
Yes.
okay? Yeah? And then you make some measurements. You obtain some results, okay? And then you can do the sequence of other operations conditioned upon the result of this measurement, okay? So if, for example, spin was up, I say, okay, now I will rotate the second spin by pi up, okay? If it is -1, I will rotate it by pi 4, okay? And this is an infinite sequence of such operations, and it's called LOCC. For some technical reasons.
So you keep one spin there and to do something
For
with
example, and it depends, and then you exchange, and what you do depends on what you did
That
before.
is perfectly understandable.
Okay.
very good. Okay,
And
then
the rest is the name.
Yeah, well,
Very
sure,
good.
I mean, we can
Thank you very much.
call it also the
Okay, so let
Chinese
me continue, please.
whatever.
Okay, so once we clarified what maximal entanglement means in some kind of resource framework, which is local operation and classical communication, we can ask how one does define maximal entanglement for multiple particles. So this is a bit more tricky. So one has different notions of maximal entanglement, and these result from different entanglement classes, which can be determined from different sets of free operations. So before we had these kind of local operations and classical communications, which are free operations, because they don't affect the entanglement. Here we could ask about different ones. But there's also another possible approach. We just ask for maximal entanglement for each bipartition of the system. So if n particles, and then we can take a bipartition, k versus nk, n minus k particles, and then we ask that these particles are maximal entangled. Yeah. And such states we call absolutely maximal entangled. So pure state phi on n parties is called absolutely maximally entangled, or AME, if every reduction onto every subset S of size up to n½ is maximally mixed or uniform. So we have the reduction rho S, and rho S has the size up to n½ and this has to be proportional to the identity. Yeah? So whenever we have access to only n½ of the particles, we know absolutely nothing about the joint state, because it's uniform. It's just completely random, maximally mixed. But at the same time, we require that the joint state phi is pure. So we see this is not quite trivial to understand if such states could exist, and for what number of parties. We know that they exist for two parties, namely the belt state. It's pure on two parties, and its reductions on A and on B, they're maximally mixed. The same is for three parties. We know there's a state, it's called the GHZ state. 0, 0, 0 plus 1, 1, 1 for qubits. It's on three parties. And now we demand that every reduction on n½ floor parties, which would be 1, is maximally mixed. And that's true. Yeah, so one party alone doesn't know anything about the joint state. This question from Higuchi and Sudbury earlier, how entangled can two couples get, is exactly this question. Does such an absolutely maximum entangled state exist for 4 particles, for 4 qubits? And the answer is no. And so the definition is equivalent to that this state shows maximal entanglement for each bipartition. Yeah? So this is the motivation why we would call this maximally entangled or not. Okay, and you can see that the question of such existence of such Ami states is a quantum marginal problem, because we are given some marginals up to size n-half. They're all identity, or proportional to identity, and we ask if a joint state that is pure exists. Okay, what are such states good for? There are a lot of kind of protocols, open destination teleportation, quantum secret sharing, holographic codes. It's not so important to exactly know what these are, but there are applications for it. Basically, every protocol that you can do with Bell state, from A to B, you can do with these states from some subset to any other subset, because there's maximum entanglement present. So some examples, the Bell states, the GH states, on 3 parties, there are some stabilizer states, some quantum code words.
What is GH?
And, oh, sorry. It's the Greenberger, Horn, Zeilinger state. It's this state. 0, 0, 0 plus 1, 1, 1. This is called GH state.
But this letters comes from
Greenberger, Horn, and Zeilinger. Yeah. So this is
kind of generalization of base state from 2 to 3 qubits. The simplest nice state of 3 parts.
Before using such symbols, it is better to explain.
yes.
Honor the people who invented it.
Yes. Okay, there's some other states, stabilizer states, quantum code words. I cannot possibly explain all of them or how they exactly work, but I just tell you there's some nice pictures. These represent states on 2, 3, 5, and 6 qubits, which are actually such absolutely maximum entangled states. Okay, so the question is, for what number of subsystems n and local dimensions d do such absolutely maximum entangled states exist?
Why 4 particle systems have been omitted here?
Because they don't exist. So that's exactly the question. For every n and d, we want to know if it exists or not. And Higuchi.
Situation when the number of these n's goes to infinity. Yeah, well, that can be the finite dimensional space, the objects, the Hilbert space, but just can go to thermodynamic limit.
Okay, so we're going to study such a question for n arbitrarily large. And then when you go to such
No, because I mean, the point is that if you have a very simple system, which is called the Ising model, right? And we know that depending if n go to infinity, the question comes that if n goes to infinity over the integers, over the odd numbers, you get the different results. If you go over even numbers, and the question is then everything will depend how I define these, how I split them, right? And we know that if the n goes to infinity over the even numbers, then the system has a phase transition in 3 dimension. If it goes over the n where these are odd, then dot doesn't have it, then you have to put the magnetic field on to remove this difficulty.
So let me answer that question. It doesn't matter for n infinity because they don't exist anyway.
If you have a very large n.
They don't exist anyway for n to infinity. Okay?
N is very, very large. Some system knows.
Okay, so I can give you a partial answer. Yeah? So if d is large enough, then these states exist for all n. So given some n, I can find such state if I tune up the dimension very large. But if I keep the dimension d fixed, there will be a cutoff where with increasing n.
You have to increase dimension d.
Yes.
When you go with n.
Exactly. And the way one rather simple bound is that the dimension has to be at least squared of n in order that they could possibly, so scaling-wise, that they could exist. Okay. Let's focus quickly for qubits. For qubits, they're known to exist for 2, 3, 5, and 6 parties, but they don't exist for n equals 4. That was the paper by Higuchi and Sudbury in 2003. And they don't exist for n bigger or equal than 8. So we see there's a gap. So what happens for n equals 7? And that was a nice question. And we have here a result that such 7-qubit AME state does not exist. It's also related to existence of some code. And we know that the...
You will be able to answer the questions if I have 137 bits.
Qubits? No, they don't. I mean, I just showed you. 2, 3, 5, and 6.
6 is on.
Okay. So, and the best approximation can have 32 out of 35 marginals maximum mix, and that's some kind of best approximation. So that question might not seem to be exciting, but it was kind of a long-standing open problem in multipartite entanglement because all other cases were excluded for a long time, and n equals 7 was open. 7 is special.
Number but 8. 6 is the diagonalic number, 7 is the same number, so now 8
Please let me continue. Okay? Please let me continue. I really, otherwise I won't finish in time. Yeah?
If and all,
7 is the same number.
I wanted to explain it, but I'm not able to because somehow. Okay, the question is, what about higher dimensions T? There's a theorem by Scott saying that an absolute maximum entangled states of n parties and d dimension exists. Then we need that n is smaller or equal than basically 2 times t squared. And the bounds are slightly different for n even or n odd. So that's an upper bound. But these bounds are not tight. And this is a necessary condition. And we have an open problem that sense provide tight bounds for the existence of such absolutely maximum entangled states. And as I can kind of shortly explain you later, there are some kind of quantum codes. Yeah, so to understand when certain quantum codes exist, this is related to its existence of such state. And that's also some kind of, these are kind of combinatorial problems which are somehow interesting for their own sake. So what we did was use tools from quantum error correction for questions in multipartite entanglement. And just very shortly, for those who know about classical codes, otherwise you don't have to understand it. A quantum error correcting code is a projector onto a subspace that can be recovered completely if only a few errors, local errors, act on it. So you have some subspace or some states in the subspace. And there's some errors, local errors acting. And if only a few happen, there's some procedure in theory that can recover the original states, such that we can encode some, say, a qubit into a larger subsystem. Some, exactly. For example, this.
0, you have 1.
Yeah, but why is error?
Oh, so
There's nothing else than error.
Something has changed or not changed?
you have to
So
decide.
what do you mean recover?
Okay, it's not so important, yeah? I can explain this later. It's just to get the feeling. It's like in a classical error correction. You have some code words, and the code words may flip, and then you want to recover the original code words. And here's the same. You have some quantum states in a subsystem, in a subdimension, and then you have some local noise, and you want to recover that. Okay.
They are punishable in some countries.
So, and the connection here is that such states are codes of distance n half plus 1. Distance tells us how many errors can we correct. Basically, if we have a distance d, we can correct roughly d half errors. Yeah, or roughly d half noises, local noises. And in that context, Rains derived an inequality called the shadow inequality, which says that for all positive operators m and n, and every subsystem, fixed subsystem t, within 1 to n, we have this following inequality. Yeah, so this looks a bit tricky, but we see how this connects to the result I showed you earlier from Butterley. So here we have the, for each subsystem, yeah, so T is fixed. There's a sum over subsystems S. You take the intersection between S and T, so this gives a minus sign. And we take the reductions of M onto subsystem S and the reductions of N onto subsystem S, and their Hilbert-Schmidt inner product is this expression. And then there's a theorem saying that this is positive, yeah, which is in some way not quite trivial because there's a lot of minus signs. This was originally used in some linear program to bound the existence of codes from the Hamming weights of the code words. So for those who know codes, otherwise don't mind. So if we use this inequality for a quantum state rho, we see that this has to be fulfilled. Huh? So we see there's a sum of minus signs over purities. So trace of rho reduced squared. This object tells us how pure the reduction S is.
What is meant?
T? Yeah, like before. T is a fixed subsystem from 1 to n. Sorry, I forgot to write this again. Okay, so fixed T, some set of subsystems. And we have this sum over all S with these minus signs, and we know that this has to be positive. In some sense, it's a non-trivial constraint on the correlations in the state. So this is an inequality in terms of purities of reductions. These objects trace rho S squared. For pure states, these objects are actually related to the concurrence, which is an entanglement measure. And so this inequality gives us constraints and correlations on all finite dimensional states. So for every n-partite state, and the local dimensions can even be different. So it can be a heterogeneous system. We have this inequality. And we know for Ame states, we know these purities, because the reductions are just proportional to the identity. So then it's very easy to calculate this object. And we can basically just check this inequality for all Ame cases. So here we have some bounds on higher dimensional absolutely maximal entangled states. That is a further 27 higher dimensional Ame states don't exist. So these absolutely maximal entangled states. And so we have again the case as before. We have the 6. This is the local dimension 2, n equals 6. The 6-qubit state exists. The 5-qubit state exists. Here are all odd number of parties, and 2 and 3 are not on the table. And then we see the old bounds, those by Scott, which say that basically the local dimension has to be roughly squared of n. So these dark blue, these are the states which are excluded before, here as well. And the light blue are those which are excluded by this shadow inequality, which constrains the correlations. These E, those are the states that exist, and we have some state which, the 7-qubit, which we excluded by hand. Yeah? So we see these inequalities somehow gives strong constraints on how the correlations can be distributed.
So which is the simplest problem still open?
Oh, yes, Carol, thanks. So the simplest problem, which we are working on at the moment, is the one of the this one, so the 4-6 level system. Yeah. So for 4 parties, we can always find such states for all dimensions, except 2 and 6, which is a bit strange. Yeah.
But since everything is finite, you can solve it writing a computer program that will search for.
Yeah, well, in principle, one can write this, a semi-definite program that searches
Runs
it.
it for 1 month and gets the approximation and never knows whether the ideal object exists or not. This is the current situation.
Yes, and in principle, this quantum marginal problem is known. You can solve it with a semi-definite program, but it's hard. It's exponentially hard, this problem. You can solve it for finite cases, but it will stop.
Too many possibilities.
The dimension is just too big. Yeah. Yeah, you can just not represent it in your computer. And if your computer gets twice as big, you can add 1 qubit maybe, but that's it.
No, not the quantum computer, ordinary computer.
Yeah, for ordinary computer, this scales exponentially because you need to represent the state in the computer.
Short comment. For this open question you are still studying, it was supposed to looking for optimizing in the space of
Okay, from this we found some new constraints on quantum marginals, which is actually this inequality. And you see now, before it was a trace inequality, and now we have an operator inequality. So it's very similar, or it's actually the generalization of the one that Butterley gave before. So we call this I of t of rho, and for a fixed subsystem t, and then we have this map here. And for every positive operator m, or positive semi-definite operator m, this inequality is satisfied. And it's again, it's not quite trivial, right? Because you have a lot of minus signs, and it's not obvious why it should be true. So as an example, if a three-partite system rho 1, 2, 3.
Is this what you have shown before in different notation as last line? E sub I, what, 2, rho.
Well, before I showed you trace inequality. So it was a scalar inequality, yeah? It was in terms of numbers or purities. And here it's an operator inequality. So it's not...
I'm talking about the last line.
Yeah, it's very similar, yeah? But this is another case than Sudbury showed. The one from Butterley showed, the one I showed you right at the beginning, had minus, 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 and plus, plus, plus. And, no, but that from Butterley is only for 3 qubits, and that's it. But this holds for any finite dimensional systems of arbitrary local dimensions and number of parties. And you have 2 to the n inequalities. So for each choice of t within 1 to n, you get an inequality in terms of operators, with a lot of minus signs which are distributed differently. So it's
So suppose I have a spin 7R, and I have a 300 of them,
yeah.
and I can calculate this quantity. What does it tell me about this system?
Well, you can
Can I
get
use
back.
it for something to tell me
Yeah,
about
I'll
the
give you
properties of this 700 spin 7R?
I'll give you an example in a second, okay? So first, to see how this inequality actually reads, because this is like a bit complicated with the minus signs. So as an example, if I choose t equals 1, 2, and I have a three-partite system, then this, what we call generalized state inversion, or this shadow operator inequality reads like this, yeah? Where again, rho 1 is tensored by identity on 2 and 3, such that it has all these matrices are 8 by 8.
So have you thought about which of them are actually essential, because you are getting exponential number of inequalities? So is it like only some of them are essential and all others can be obtained from this essential set?
I don't think that.
Because
So some of them.
The problem is this non-overlapping quantum marginal
Yeah.
that you are getting exponential number of inequalities, and then it turns out that actually most of them is rubbish.
Yes. So for pure states,
But you can derive them from the set, much smaller set. They are simply redundant. So the procedure gives you a lot of redundant inequalities. Yes, so they give you no further
That's
information.
what I expected. So in other words, you can derive arbitrary number of inequalities, and they are
Well,
produced.
I can tell you for the AMI states, it's not clear which one are the most important, because they're not all giving you contradiction, but some do and some others don't.
Somehow, I know, try to understand how to extract those important.
For a given state, I cannot tell you the exact way to extract which ones, but what we've seen is that there's not just one of them which is important, it can be different ones, depending on the context. For the AMI states, for different choice of t, you get sometimes a contradiction, sometimes not, and the subset t it's not clear which one you should choose. Okay? So this would be the generalization of this result by Butterley. If a set of marginals rho s of size n half minus 1, n minus 1 are compatible with a joint state, then for all t within 1 to n and t odd, this is positive. So here you don't have the joint state. Yeah, so rho 1 to n is not included because we only have marginals up to size n minus 1. And the sum of subsets is strictly, it's strictly a subset of 1 to n. And
Is there any physical information which I can gain from this inequality? I mean, I'm
So here it,
If I have a real physical system,
so here it gives you three, for qubits, yeah, for 3 qubits, the smallest kind of non-trivial example, you get 3 extra constraints than before. So Batelet produced this constraint, and this inequality just gives you, like this, 3 extra. And you get exponentially many, with n.
Maybe I can comment a bit about the applications of these inequalities. So if you, for example, have a Hamiltonian and you want to have one state of this Hamiltonian, this is a many-body Hamiltonian, and assume that interactions between your particles are just two-point interactions, so that only pairs interact. Then the problem of finding a ground state, so this is a minimization of energy. So either you can minimize over all pure states of n particles. This is then the dimension of this space scales exponentially with the number of particles. Or because these are only 2 particle interactions, you can find the same minimum using 2 particle reduced density matrices. Then your space is much smaller, but you have to know how to bound this space, because not all 2 particles.
so for variation,
Exactly.
For
So
variation,
you take a
it
complexity.
allows me to choose proper set of the quantity over which I vary.
Exactly.
And that is good.
And this is actually how this problem originated, because it came from quantum chemistry, where they
Yeah,
wanted to find this kind
I
of
had
things.
that feeling that the quantum chemists must,
Yeah.
they are busy with this.
So thank you. That's I should have mentioned this at some point when I mentioned Coleman. That was the original question.
For example,
So
prove or simplify all this variation like they can all the
So for those who know about universal state inversion, maybe you do, this inequality generalizes the universal state inversion, which is one of them, and this is the generalization which I presented you. This map, I of t, represents a fine graining of the so-called reduction map. So in some sense, it's also a generalization of this map. Rho maps to 1 minus rho, which is used for entanglement detection. Okay. And because this map is positive, but not completely positive, that means one can, in principle, detect entangled states with it. So if I apply one tensor, this map, to some bipartite quantum state, or actually n-partite, but I cut it in some way, then I know rho is entangled. So this map generalizes a lot of known concepts in quantum information for entanglement detection. This universal state inversion, which was used to define the concurrence, entanglement monotones, and so on. And you see that the shadow inequality represents a constraints of correlations, because we can also rewrite this in terms of linear entropies. So in some sense, it's also information theoretic inequality, where we take the information of the full state and then take the entropy of the subsystems out, and then the smaller again in some kind of inclusion-exclusion principle. So a similar inequality, but with this. So just the von Neumann entropies, Shannon defined as so-called interaction information. And there it can be either positive or negative. But the first order, in terms of linear entropies, we know that it's actually non-negative. So it has some kind of also information theoretic understanding in some way. So we get exponentially many correlation constraints and compatibility conditions for subsystems. Quick examples to see what one gets out of it as well. For those who know some inequalities for von Neumann entropies. So there's this strong subadditivity, which was very famous, derived by Lieben-Ruska in 1972, and which is equivalent to this weak monotonicity. And we see that we can get a similar inequality, but in terms of linear entropies, with the help of this shadow inequality, with some correction term. And we can also derive some kind of Araki-Lieb-like inequality. So this was known as Araki-Lieb inequality, this part, for Neumann entropies. And this is the subadditivity. So it's some kind of information theoretic. We know that the entropy of the joint state is smaller than the entropies of the individual states added together. Okay. So these were known. But it's nice that one can derive it in a very straightforward way. Good. So, summary of the results of the talk. Arbitrarily strong quantum correlations are not allowed. In the case of qubit states, these absolutely maximum entangled states only exist for 2 parties, 3 parties, 5 and 6. We have some constraints on higher dimensional, absolutely maximum entangled states, and we get exponentially many correlation constraints in terms of purities or linear entropies on the distribution of entanglement of multiple tight quantum states. And we have this new shadow operator inequality that generalizes the inequality derived by Botticelli with some interesting applications for the quantum marginal problem and also for entanglement detection. Okay, references, and thanks to collaborators. I think the beamer just died. Okay.
Are there any questions?
So I'm
Please.
completely out of this field of cosmologist, but I try to guess if I get it right, at least one of the results, that you show that the AMI state 7 is basically excluded because it has the local communication equivalent to the states with 6 qubits as well. It's the same, so that's why it's
Can you repeat?
for the 7 qubits, you said it was unknown before, but you have shown that this is excluded for the
Yes.
And how this results was achieved?
Oh, this is a bit a technical thing. But, well, actually not. You just need to understand anti-commutation relations between Pauli matrices and some kind of see that how the spectrum is of these. So the marginals of these states are always projectors in some
So the
sense.
graphs that the graph of 7 was equal to graph of 6, so I missed that part.
Oh, no, this was also 7. It was just a different, yeah, it was a wheel with a center. But these are local computation equivalent. It's for, okay, if you know what graph state is, it's now funny because you don't see it, but yeah.
I just have a comment. Years and years ago, there were these quantum mechanics and quantum manifolders like Feinberg and Yanovich. They wrote the books about the properties of reduced density matrices. So would that then be interesting to have kind of those books where they haven't got results comparable? And surely, of course, in most of the cases, they work in infinite Hilbert spaces where they want to solve the problem. I don't know, PCS, for example. Right?
No, so indeed, some of those older quantum chemical papers become known again, and they are quoted in our community. Like Felix started on this Coleman paper from 60s.
Yeah, that's the chemistry paper.
Yeah, that's good, certainly.
Norman, yeah.
So the original interest indeed stems from quantum chemistry.
Yeah.
And we somehow appreciate this.
Yeah.
On top of that,